Welcome to the 6th lecture of the course. We'll be talking about entanglement in quantum spin chains. What we do this morning will go together with the tutorial in the afternoon, as we did last week. And today, we want to do two things. One is to actually start studying entanglement in not just a bipartite system, as we saw yesterday, but instead in a system made of many, many parts. That's one thing we want to do. And the other one is to get ground states of spin chains for a number of spins which will be significantly larger than last week. Roughly speaking, twice as large. Okay, so what do we want to do? We want to study entanglement of a state. The state is not a state of two parts A and B, but a state of, say, n spins. So the state of n spins, spin 1/2 degrees of freedom, can be expanded in a local basis, right? Each I here runs from 1 to 2, or up, down, or 0, 1, whatever your favorite way of denoting a basis of two states is. And what we want to study then is some properties of the entanglement of this state, but we will use actually only bipartite entanglement applied to partitions of these n spins. So what I mean by this is that if we have the n spins in here, in a one-dimensional arrangement, we could ask what's the entanglement between this part and this part. Okay? So bipartite entanglement between one spin and the rest. Or also, another question we could ask is what's the bipartite entanglement between two spins and the rest, and so on. Okay? 3 spins and the rest. Okay? So what we'll do is we'll have several bipartitions. I'm going to call this A1. This is A2. This is A3. I'm going to call this B1, B2, and B3. Okay? And for each such bipartition, I'll compute the entanglement of the state under consideration. And so what we have is then that for each partition, for partition AN Vn, okay, we can compute the entanglement entropy, which will be given by the reduced density matrix on, say, part AN. Okay. And actually, what we're going to do from this, we will always take partitions where the spins are together. So, and we'll count how many spins we're putting together. And so we'll be talking about, you know the definition of this. This is equal to minus trace of rho AN log 2 rho AN. Okay? And now, from here, we'll just focus on how many spins we have. Let me call it L. Number of spins in AN. Okay? And we're going to be studying, we're going to be plotting this entropy, which now only depends on L, on the number of spins, okay, as a function of L. Okay, so L equal to 1, L equal to 2, 3, etc. And we'll get some values for the entropy. And what we are going to be interested mostly is in understanding what function we get as a function of L. Okay? And what's going to be really important is for large L. What happens for large L? What type of scaling, asymptotic scaling for large L we get? That's going to be the most insightful quantity that we will be studying today. Okay, so we're back to our notebooks. I need to start my computer. Ideally, we would like to study a case where the total size, the size of the lattice is infinite, just to be able to focus only on L, the size of the small region. But in practice, we'll deal with whatever we can. So today we'll be dealing with n, the total system size, on the order of 20. And part A will have 1, 2, 3 spins in it. Can I have the projector on, please? How do I ask for this? Hi, can I have the projector on, please? Thank you. Okay, so please open your notebook. It's called iJulia 5, meaning it's the fifth of those. Entanglement in quantum spin change, which you probably received yesterday. And the first cell contains this using pipeplot, using JLD, and using linear maps, which hopefully works for you. After you've installed all the necessary packages. Okay, and this is almost working. All right, there we are. Okay, so yeah, I'm gonna shift enter this cell, and hopefully nothing happens. Just taking a couple of seconds. And what we're gonna do first is we're gonna generate a random state of n qubits for n equal to 20. And we'll use this way. So we need to generate 2 to the n complex coefficients. Then we'll normalize a state. That's this. We divide psi by its norm. And then we reshape it into matrix A, okay, which will be in this case for correspond. We're going to make a partition where the first part is 3 spins, and the second, or 3 qubits, and the second part is 17 qubits. And so, if you remember from yesterday, then the reduced density matrix is just A times A prime. Okay? Do you remember this from yesterday? Very good. So, and then we have a function here. What we want is to compute the entanglement entropy for the reduced density matrix. And the code should have a back. So let me show you. Well, anyway, let me tell you first what this should be doing. So it takes the density matrix, it diagonalizes, so we know the eigenvalues. And then the back is here, so let me correct this. Instead of size of D, it should be size of U. We look at how many eigenvalues we have. And then what we do is, for any, we have a loop here. We're going to store the entanglement entropy in this variable called EE, starting from 0. And we're just going to loop in there and add from each eigenvalue of the density matrix the contribution to the entropy, okay? As given by the minus the eigenvalue log 2 eigenvalue. And we do this only for positive entries, because if we try to compute if there was a 0 here, okay, there was a 0, then so 0 log 0, this one would complain. The log of 0 is minus infinite. Okay, so let's try this. And here we have it. We've computed the entropy, the entanglement entropy between 3 spins, or 3 qubits, and 17 qubits in a random state of 20 qubits. And the first observation is that this number is 2.9999. Let's run this again and see how this entropy depends on the initial state. We are generating the state randomly. So remember, it's 2.99995. We run it again, and it's different state. is 2.99995. So I should be paying attention to the next digit, which is actually changing. Let me run it again. So I go back to the cell, Shift Enter. Okay, it changed 99996. 99996. So it's changing, okay? But we see that it's always very close to 3. Now, what's the maximal entropy we could have in 3 qubits? Three qubits. So let's do this. Remember, if I give you a probability distribution with chi different values, okay, the entropy of this distribution is at most, you can prove that as an exercise, is at most the entropy of the distribution where each of the entries is the same. Okay? But how much is this one? Well, this one is minus 1 over chi log 2 of 1 over chi. And we have this chi times, right? So chi goes away, and this is log 2 of chi. Okay? Now, how much is chi? Chi is the number of the size of the vector, probability. And in 3 qubits, so n equal to 3 qubits, right? We have a density matrix of dimension 2 to the n equal to 8, right? So in general, let's say, yeah. So let's call it L, since we're going to be talking about the size of the region. And so more generally, this is chi, right? Chi is going to be 2 to the L. So what's the entropy of the entropy as a function of L is going to be upper bounded by the entropy of 1 over 2 to the L, 1 over 2 to the L, 1 over 2 to the L, right? And this is nothing but log 2 of 2 to the L, which is equal to L. Okay? So the entropy of L qubits is at most L. Okay? That's actually why we use log 2 in our definition of the entropy. Okay? So what we're getting here is L is equal to 3, and we're getting an entropy which is very, very close to 3. And we've tried this a few times. You can try it as many times as you want. Any random state that you generate will typically have an entropy which is very close to 3. Okay? Very good. So we'll continue thinking about that later. Now what I want also us to think is, one more thing before we continue. So let me go to the next cell. Now we've generated the entropy. We've computed the entropy of a single interval of size 3. Now we could write some slightly more complicated function that will, given psi, will compute the entropies for all the intervals. Okay. And for computational reasons, I'm going to stop after we get to half of the chain. So I'm not going to compute the entropy of more than half of the qubits, because it would take too long. We would have to build a reduced density matrix which is too large, right? So in here, in this sequence, if A4 will take 4 qubits, A6 would take 6 qubits. But actually, if I really wanted this entropy, I could compute the entropy of B, which would be smaller, right? So it would be a smaller metric. So if we stop at half of the chain, this function will already do everything we need. Okay, so this function is very simple. Given psi, which is a vector of 2 to the n components, it will look at how many bit qubits this is, n, and then it will take p, which will be n half or n minus 1 half, depending on whether n is odd or even. And so p will be the largest size L that we want to consider. And then we have a loop from 1 to p, right? It's a loop over the size of part A, 1 to all the way to p, which is either n half or n minus 1 half. And then for each value of p, we can compute the entropy. And that's happening somewhere here. And at the same time, since we are diagonalizing the reduced density metrics for 1 spin, 2 spins, 3 spins, etc., we can just keep the eigenvalues, which are what we call the entanglement spectrum, okay, or the Schmidt coefficients. So this function returns both what we can call entanglement spectrum or Schmidt coefficients and the entanglement entropy for each of these partitions that we just discussed. So why do we do this? Well, it's like scanning. So let me shift enter this. Okay, no typos here. And then let's just apply this function and plot the results. So here we again start with n spins or n qubits. We start with a random state, and then we normalize it. We compute this entanglement spectra and entanglement entropy, and then we plot them. Okay. Okay. So the result is here when it comes. All right. So let's have a look. Let's start with this one. So this one here we have L. This is a plot of the form I was telling you. We are plotting the entropy of a group of L qubits as a function of L. Okay, and what we see is that in the random state there is almost a straight line going up, and if you check, actually, for 1 you get entropy 1, for 2 you get entropy 2, for 3 you get entropy 3. So we are saturating this bound most of the time, all the way. And up here you see that actually it's going down a little bit with respect to a straight line. But essentially, if you take a random state, what you realize is that the amount of entropy in a subset of n qubits is, or L qubits is L. Okay, it's proportional to L with the maximum possible proportionality constant, which is 1 in this case. Okay, so that's what we have here. Okay, the entropy. Think of this really as a scan of the state as far as entanglement is concerned. We look at the entanglement between all possible bipartitions. And here what you have is the entanglement spectrum, or the eigenvalues and Schmidt coefficients of this partition. And what you see here, for instance, is that for the first partition, you have some number of eigenvalues, which are very similar. Here, these are 2 qubits, so here we've plotted 4 eigenvalues, okay, of the reduced density metrics. But you only see one plot because they are essentially identical. And here there should be 8, 16, 32. And at some point they start diverging a little bit. But you see that all the eigenvalues are basically the same. That's consistent with the picture we had, that if we wanted to saturate the entropy, all the eigenvalues had to be the same. Okay? Very good. All right, so we've been discussing properties of n spins and qubits for n equal to 20. And the question is, why didn't we manage to diagonalize the Hamiltonian of the spin chain for n equal to 20? Why did we have to stop at n equal to 10 if it turns out that we have no difficulty in manipulating wave functions of 20 spins? Okay, so we've been right now been studying 20 spins, the wave function on 20 spins. Why can't we diagonalize the Hamiltonian, find the ground state for a Hamiltonian of 20 spins? And so let's see why. Let's review what it takes. So let's look at the computational cost of finding the ground state. Computational cost of finding ground state. of n spins. And you've done this. Now we just want to think about the cost of it. Okay? So the first option is we invoke ache of h, right? The function ache of h. And this requires building h, which is a 2 to the n times 2 to the n matrix. Okay? And so let's talk about memory. And let's talk about time. These are the two variables, computational. So if we want to characterize the computational cost, we want to talk about how much memory we need, how long it will take. And memory, well, it's clear. We need 2 to the 2n coefficients just to write the Hamiltonian. Okay? 2 to the n coefficients. And time, if you remember, multiplying two matrices of size L was L to the third power. The size here is 2 to the n. So it will take just multiplying. So the time to multiply, that's coming from multiply h times h, which is what happens in Ike. Okay, a way of solving, of diagonalizing a matrix is by doing matrix multiplication. And so this is going to be order 2 to the 3n. Okay? If the matrix is 2 to the n times 2 to the n, multiplying two such matrices will take 2 to the 3n. Is that clear? If it's not clear, tell me, because we're here to learn. Yeah? Okay, so this cost with your computer allows you to consider n equal to 10 to work comfortably, to get results within a few seconds. You could push it a little bit. Very good. But, so this was one strategy. But we also considered another strategy, which was if we just want the ground state, we don't need to diagonalize the whole matrix. Instead of calling ache, we were calling aches. Okay? In this case, we still first had to build a Hamiltonian. Okay? So I'm just going to say we repeat this. And so the memory there is 2 to the 2n. But ache doesn't work by multiplying the Hamiltonian. It only requires multiplying with itself, but multiplying a given state times the Hamiltonian. Okay? So if this multiply the Hamiltonian, if this is something that we can express as in diagrammatical notation as multiplying these two matrices, this one consists in multiplying a vector times a matrix. This was 2 to the n, 2 to the n. These indices were taking 2 to the n values. Here, 2 to the n and 2 to the n. Okay, so this cost here was the product of these indices. Now we only have these products. So the cost here is going to be 2 to the 2n only. Okay, I'm saying ache is based on multiplying matrices. Aches is based on multiplying a vector times a matrix, and the cost went down. Okay, so we had the cost 2 to the 3n, which allowed us to consider n equal to 10 spins comfortably. Now, with cost 2 to the 2n, we can comfortably, say, deal with 15 spins. Okay? That's because the memory was not the big deal. The time was the big deal. So we still have the same memory requirements, but we've managed to lower the time. Okay, so this actually was the smart way of doing things, but we didn't exploit all that we had, because it turns out that there is a better strategy here if we take into account that the Hamiltonian is sum of local terms. Okay, so we may not need to build a whole Hamiltonian if all that we need is to multiply a vector times the Hamiltonian. So Ikes today we'll use Ikes, but in a way where H will not be built explicitly without, so X without building without building this 2 to the n times 2 to the n matrix explicitly. Okay? All that X wants is to know how to multiply a vector times H. We don't need to build the huge matrix in order to get that done. So we're going to exploit that the Hamiltonian is just a sum of local terms, nearest neighbor terms. Okay? And we will try to understand how to multiply the Hamiltonian, a vector times the Hamiltonian, without ever building this big matrix. And so how does this work? I'll specify it in more detail in a second. But if this is psi, psi has a number of legs, meaning we are using this notation where a tensor, see on the very top, we have psi and a tensor with n legs there, psi I1, I2, In. So let me just draw this here, I1, I2, In. That's the state. And if we want to multiply this times H, a possible term here is going to look like this. This is psi, and now we take these two sides and we multiply it by H 3, 4. Okay? So that would be one term in this expansion, and we'll have to do this n times for different terms. But to multiply these two guys, I never had to build the Hamiltonian. Okay? The large matrix for the Hamiltonian. Is that clear? So this is what we want to do, and in this case, if this multiplication amounts to, after some reshaping, this is our H 3, 4, and then here we have our psi. Okay, and this index here is 2 to the 2 values. When we put these two indices together, we're going to be reshaping the tensors. And there are two more indices, 2 to the 2. And if we look at this, we have 2 to the n minus 2 legs, which correspond to all the legs that are not that we are not acting on with H. And now if we multiply this to understand how costly it is to, so if we want to understand the cost of multiplying this this matrix times this matrix, we just need to multiply these indices. And so the cost here, and this is becoming messy, the cost here, this time is 2 to the n plus 2. Okay, I just multiplied these three together. So we went from 2 to the 3n to 2 to the 2n, and now to 2 to the n. Okay? And then we'll have to do this n times, because we'll have to do that for each Hamiltonian term, so there will be an n here. All right, so let me highlight this then. With exact diagonalization, by building the Hamiltonian, we had this cost. If we just want to multiply the Hamiltonian times a vector, we had this reduced cost, and now we just, if we don't even build the Hamiltonian because we exploited the sum of local terms, we have this smaller cost. And that's how we're going to get to n on the order of 20 comfortably. Okay? Very good. So let me review this algorithm a bit more in detail. I see. Oops. So what we have to do is we have to consider what I just did for, so I'm gonna write this again, but more carefully. So we have n Hamiltonian terms, and so we have n Hamiltonian terms. We have H1, 2, have H2, 3, all the way to Hn1. And for each Hamiltonian term, we want to do something similar to this. So let me consider just the first one. Okay, so what we say is we want to compute H times psi. which is equal to the sum over I, hi, I plus 1 for psi. Okay? And what we are arguing is that doing this has a cost, which is it's just the cost of this is just 2 to the n plus 2, and we have to do this n times because there is a sum here. Okay? And now we want to write code for all this. Okay? And this is what we're going to do next. So there are two methods that we will consider. One is called power method, and the other is called Langsos. And both of them are based on multiplying our state by the Hamiltonian. The Hamiltonian, so the two-side Hamiltonian is it's all that we will need. Okay, but to diagonalize to find the ground state of a Hamiltonian on n sides. Yes. Okay, so let me see what's. Yeah. All right. So what we want to do then first is to write a function that performs this multiplication, psi times h, 2 or two-body term, and so. First, what we do is we build our two-body term, and this could be either for the Ising model or for the XX model, the two models that we considered last week. Okay, this is just taken from last week, and if I run this, I find indeed the two-body terms corresponding to the Ising model here and to the XX model. Okay, and now I want to write a function that multiplies h and psi. Okay, and this function is written here, and there are some reasons that I don't want to discuss now why we have to define a new psi as an input. This is basically we are writing this function in a way that later we can call some package, these linear maps, and we can take this function and put it there so that we can use Ix to find the ground state. So this justifies certain aspects of how this function has been written, but they are not important. The part that is important is that one of the inputs is a vector, psi, and that then it looks at how many qubits this corresponds to, okay? And once we know how many qubits we have in here, there are two quantities that are important. One is this dim psi. Dim psi. This dim psi is just a tuple of, so that's n different 2's together. That's because we will want to take this 2 to the n vector and reshape it. Okay, we're going to use this for reshape. The function reshape, so that we will take psi as a single vector with 2 to the n, with an index that takes 2 to the n values. We want to reshape it into this other expression. Now this is a tensor. It has n indices, okay? N indices, each one taking 2 values only, okay? So we need this dim psi. This will be what we input into reshape. You have it right there, okay? We'll take psi and we'll reshape it so that instead of being a vector with 2 to the n components, now it's a tensor with n indices. That's one thing we need to do. And then there is this other cycle permutation, which actually is another tuple with 2, 3, n, and 1 in there, right? There are n entries again. And this one, we'll use it to perform a permutation. So we'll use it for, so this is, let me find it for you. We'll use it in permute dimensions. There is a function called permute dimensions that is going to take our tensor psi with all the legs, and it's going to permute these n indices according to this permutation. So what this means is that the new first index will be what used to be the second one. Second index is going to be what used to be the third one, and so on. And then the first one is going to be the last one. Okay? So this is another building block that we'll be using. We're going to permute the indices. It's like making a translation in the spin in a ring. Okay? We're going to shift by one all the indices. Okay, so with this, we can now try to understand this function. What it's going to do is the following. What we would like, let me consider the simple example of n equal to 3 to explain it better. So actually, what we're after is we want to take psi and put the Hamiltonian here. So this h, it's called h2. Okay, it's always the same term. We would like psi also with this term acting here. And finally, psi with this term acting here. Okay, so this is what we call multiplying psi by h. Okay, it's the sum of acting with the two-body term 3 times on different pairs of spins. Okay, this is what we would call the result, psi prime, or n, psi prime, which is equal to h times psi. Okay. Okay. So we would like to do that. That's what this function should be doing. Okay. And we'll do it in the following way. We're gonna actually do it in this way. Psi, we'll act on psi with a two-body term. And you can imagine that you have another copy of psi, and at this point you don't do anything. Okay? And you have another copy of psi, and again you don't do anything. Now I'm going to do something else, which is I'm going to permute. I'm going to take the first index to the last one, and I'm going to do the same here. Okay. Then I'm going to do nothing on the first copy. I'm going to multiply by h2 on the second copy. So this is h2, and I'm going to do nothing on the third copy. Now I'm going to permute the indices. And finally, I'm going to do nothing on the first copy, nothing on the second copy. I'm going to apply h2 on the third copy, and one more permutation. So the first index sent to the last one, and so on. Okay, and if you look carefully, the result of doing all this is the same as the result of adding these three terms. okay? But I've just rewritten things in a way that what we have to do at each single step, we have to repeat a sequence of things. So we have to first apply H2 on the first pair, then a translation, a rotation. Then we have to apply H2 on the first pair and followed by a rotation. Okay? And it's always the same. I'm always applying H2 on the first pair and then performing a translation. Good. So this is what this code is doing. And with this explanation, if you now look a little bit carefully to the code, you'll see that. So what we have is, initially we have psi, which we know what it is, okay? And we have n psi, which is the new psi or psi prime. And what we do is we take psi, we reshape it as a matrix. This is the trick we discussed before. We want to multiply psi with H2 acting on the first two spins. So what we do is we reshape this in such a way that these are 2 to the n values, 2 to the 2 values, 2 to the 2 values for these indices, and this 2 to the n minus 2. Okay? So we reshape psi in this way as a matrix. That's this expression here. Then we do the same for the new psi. Then here we perform this operation, H2 times psi. This is H2 times psi, okay? And what we say is the new psi, psi prime, or n psi, is equal to what it used to be plus the product, this product, okay? So this corresponds to this term here. Psi prime, we just added to psi prime this term. Now what we do is, okay, we reshape things back to having n legs for both psi and psi n, and then we permute the dimensions. We apply this translation, okay, by one side. And then this is our loop. So this is the loop over n. We do this n times, capital N times, and we are just producing these copies. And we are adding in the first round of the loop, we add this to psi prime. In the second round of the loop, we add this to psi prime, okay? And so psi prime in the end is going to be the sum of terms. Okay, so hopefully that is sufficiently clear. If not, please have a look. And if you have questions, you can ask me later. But that's what this function is doing. And then I think we're fine with time, but let me see. So now that we have this function that will multiply psi times the Hamiltonian without ever building the full Hamiltonian, we can try how this works. What we can do here is choose a Hamiltonian. Right, we make a choice of Hamiltonian. Say we choose the Hamiltonian, the Ising model. Okay. I don't know why this is here. Let me kill it. And then what we do is we're going to be using the power method. So let me quickly describe what the power method is about. Now we have the ability to take the state and multiply it by the Hamiltonian. So what is this going to do for us? Well, imagine we have psi, okay? And H can always be diagonalized. So there are eigenvalues and eigenvectors. And here I'm going to assume the following. I'm going to assume that, so n goes from 0 for the ground state to 2 to the n minus 1. I'm going to assume that this is the ground state energy. I'm going to assume that it's smaller, so there is a finite gap in the energy. And then okay, these are the energies. I'm going to assume also that it's the largest one in absolute value. Okay, so this trick we have to make all the energies negative. so that the ground state energy is the one that has the largest absolute value. We've done that in the past, last week. Okay. So we can accomplish this by just shifting the Hamiltonian, okay, by some finite amount. Good. So if we have that, then let's think about psi. We can always expand it in this basis, psi n. And so what we want to think about is what happens if we multiply psi by h. So this is simply, this coefficient will be modified by the energy. Okay? And if we multiply many, many times, if we keep multiplying to, that's unfortunate, what's a different number? P times, okay, times psi, then what we have is that the wave function has become psi n e n to the p power psi n. And now I want to argue that this is basically, for large p, this is going to be basically the ground state. So how do we see this? Well, we can expand this as psi 0 e0 to the nth power. And this multiplies both the first term in this expansion, the e0, and the rest. And let me write the rest as psi 1 over psi 0, e1 over e0. There is, p power, right? Okay, and what you see here is that indeed, remember that E1 in modulus, E1, E0, that's smaller than 1. We just assume that there is a gap, and now we have the power P. So something smaller than 1, you take the power of it and becomes smaller, exponentially fast in P. Okay? So by multiplying the state, the initial state, with a power of the Hamiltonian, or by the Hamiltonian many, many times, we're collapsing the ground state, the initial state into the ground state of the system. Is that clear? Good, so that's what we're going to do here with this power method. And so what we do first is we start with a random. I'm going to run this with n equal to 10, so only 10 spins. Don't be too disappointed. We could run it with larger number of spins. It will just take longer, and we don't want to waste time. But we prepare state randomly. We normalize it, and then here what we're going to do is just test how long it takes for this function multiply h psi to multiply h and psi. To know how long it takes, we just introduce this at time in front of the expression that we would like to measure how long it takes. And we see that it takes 1 second. Let's try it again. OK, that's more like it. So it doesn't take much. OK. Let me try it again. Yeah, it takes less than or a couple of milliseconds. So we can loop over this. And so now that's what we're going to do. We have a loop here, and it's going to take psi as an input, and it will multiply by h. And that's going to be our new psi or psi prime. We're going to look at how much the energy is. We're going to plot, we're going to keep the energies in this variable. And then we'll say, OK, now psi is the new psi prime, and we'll compute again the product of h times psi, right? So this loop is just computing this application of h on psi a number of times. And then we can arrange it, so we can plot the results. And let me just run it and tell you what these plots are about. So here you get the result. You see two identical plots, or almost identical. Yeah, identical plots at this point. This is for all the iterations, and this is for only the most recent iterations. This is because we can actually run the cell again, and this will change. Anyway, let me explain it here. So what I've done is I've plotted the energy of the state as a function of how many times you've applied h to it. Okay, so this is the original energy after applying h to psi once, h squared to psi, h3 third power to psi, and so on. Okay, and what you see is that the state that we get has lower and lower energy. Okay, and it's going down, and now it seems to be converging. And on this side, what you have is the most recent iterations. Every time you run the cell, it doesn't start from scratch. It keeps the final psi of the last run as the starting point. And so here we just plot the last 10, so from 11 to 20, right? This is h to the 20th power applied to psi. It gives you a state with this energy. And we can keep iterating this. And so, for instance, if I come here and I say, instead of 10 steps, apply 1,000 steps. Okay, so something early happens. This is just to see, yeah. And this is the final result. So after 1,020 steps or something, we have this ground state energy, which is pretty stable. And this is just the last 1,000 steps. And so what we see is that we've been able to manipulate this wave function and bring it down to the ground state without ever building the whole Hamiltonian. Okay? So that's the conclusion here. This is, I ran it for 10 more steps just to show you that in the last 10 steps, the result was some number, okay, up to corrections in the 7th digit. This refers to the 7th digit. Only the 7th digit is changing. So we have essentially converged to the ground state. And you can keep running this forever, or well, until you reach, until instead of 7 digits, you get the numerical precision, and then you stop. Okay, so this was a demonstration that this is possible, that you can build a wave function for the ground state without ever constructing the whole 2 to the n times 2 to the n matrix for the Hamiltonian. This is a demonstration. Now, once you can do that, once you know how to multiply h times psi, there are, when we have the ability to multiply h times psi, there are smarter ways of using this ability to converge faster to the ground state. And Langsos is the name of a method that is smarter. So basically, Langsos, which we will not discuss in detail, okay, Langsos is just taking psi, which we started from, h times psi, which we computed, h squared times psi, and so on. And this, it takes this after p steps, we have hp psi, so we have p plus 1 states, and this defines some subspace. And what Langsos does is looking at this subspace, and it projects the Hamiltonian on this subspace. Okay, the Hamiltonian lives in this huge space, but you can project it down to a p plus 1 dimensional subspace and diagonalize it there. Okay, so after 20 steps, you have 21 times 21 matrix, which you can diagonalize, and it turns out that that's a much better way of finding the ground state. Okay, so that's all you need to know, that there are better ways of finding the ground state. Once we have the ability to multiply h times psi, and here we're just going to use a package called linear maps that only requires, so actually Langsos is what X is going to implement for us, okay? We don't need to know how to use this ability anymore. We just need to tell X that we know how to multiply psi times h by this command. H is linear map, okay? And then here we just input our function, the function that actually multiplies psi times h. And this linear map then explains to X how to do this, okay? So if you have a different Hamiltonian, you can change h2, and then just with this command, h equal to linear map of multiply this function and some other information, then you can just call X to find the ground state of the Hamiltonian. Very good. And if we run this for 14 spins, it's going to take a few seconds. And there we are. At time is measuring how long this took. And we see that it took 10 seconds. Let me try once more. I think my desktop was faster. But anyway, on my desktop, it took 4.5 seconds. Now it's 7. OK, so my laptop is slower than my desktop. Very good. But you could actually go higher and higher. N equal to 16, N equal to 18. You could do N equal to 20. Don't do it during the class, because it will take several minutes, maybe more than that. But in principle, you can achieve that. Very good. And the last two things that we need to know for this afternoon are the following. We don't want to diagonalize 20 spins, take, say, half an hour, and then lose the final wave function. Okay, we want to store the final wave function so we don't have to run that diagonalization algorithm for half an hour every time we want to play with this wave function. So here's something very simple you can do. You can store or save your wave function. So at the end of here, we've called the wave function psi and the energy E. So we're going to store in my file Julia data, or JLD. This is the name you want to give to. There will be some dictionary that there is some format in which this is saved. What's important is that psi here is what you want to store, okay, and E also. And so if I do this, this one, yeah, it can be anything. Yes. Okay. So, and this thing here is just the name that you want to call this variable when you want to load it down here. Okay, so we've saved this. Now we go home. Okay, and the next day we want to retrieve or recover this psi and E, say psi. So that's the way you do it. You can load it from the file where you store it, and then psi is precisely the label that you gave it here. So instead of psi, we could call it QQQ, okay? And then down here, we would write QQQ if you wanted to recover psi, okay? And so here you have the variable, which is this array. Okay, it's a large array. This is the size. It should be 2 to the 14, I guess. Okay, so, and then once you have it, you can just go ahead and run the function. Remember that before we've written a function that computes the entanglement entropy for different bipartitions. And so that's the result of plotting it. We see that this time we don't get a straight line as we had for a random state, but some other curve. And this afternoon, we'll start playing and try to understand what this curve is trying to tell us. Very good. And for this afternoon, you'll probably, in the tutorial, I've sent you two files, data files, one called Ising and one XX. Okay? And so for the tutorial, instead of spending time, these are for 18 spins. It took like 3 minutes to run, but still, I want to save you 3 minutes every time. And so when you want to analyze these wave functions, you just load them. Okay? Very good. I finished on time. Are there questions?
The approach, you use the linear map package. Where does it specify what P is?
P. Yeah, you don't need to know. That's something.
Does it decide by itself?
Yeah, so it wants to give you something that has converged, right? So imagine that here you try with P equal to 5, you get some energy. You try with P equal to 6, you get a lower energy. And the difference between the two energies is larger than some accuracy that you want. Then it will keep increasing P. So the result is guaranteed to have some accuracy, and it took the P as large as needed.
So this doesn't need an equal state either?
It does. I think it's through. It starts. Yeah, it decides on the random initial state. You can probably decide what the initial state should be, but that's, yeah. We take it at the simplest possible level here, where the decision will be made randomly or something. More questions? Okay, so see you this afternoon.